Thank you, Jens. I also would like to thank Carla and the whole team for putting up this conference, which I can imagine was a lot of work. I will talk about strong field physics in condensed matter, what's qualitatively new there, and this is work done together with the PhD student Christoph Jürs and the master student Daniel Moos. So let's make a list. What's different between laser atom interaction and laser solid interaction? And I'm really thinking about crystalline solids, so not liquids. So obviously in the atom, there are rather few electrons. In a solid, there are really many electrons. We, in laser atom interaction, prefer to think in position space, whereas the condensed matter people prefer to think in crystal momentum space. And of course, there is a reason for that, but there might be situations where it is not adequate to think in K-space, for instance, if edge effects or surface effects come into play. And we talk about tunneling in laser atom interaction as the first step in the famous three-step model. And somehow this corresponds to transition between bands in solids. Can we talk about tunneling there as well? I'm not sure. Then the free motion, so the second step in the three-step model, is governed in the laser atom case simply by this Hamiltonian, where K is replaced by K plus vector potential. And then you have here essentially the kinetic energy with the momentum replaced by P plus A. And something similar happens in solids. You have a Bloch Hamiltonian, which I will derive soon for you. And then, provided you made the correct Bloch ansatz, you can replace in this Hamiltonian also K by K plus A in order to couple to a laser field. However, if you don't make the correct Bloch ansatz, this is actually not true. Then the third step is rescattering or recombination. So what about rescattering in solids? This is already built in. If you are working with Bloch states and the Bloch Hamiltonian, the fact that the electrons scatter at a periodic potential is built into the formalism. So again, this is included in the Bloch Hamiltonian. And then there is this recombination step. And this can be thought of in a solid of a recombination of electron that was promoted to the conduction band with a hole in the valence band. And John mentioned this already. So this is a K-space picture of the three-step model. Then in the atomic case, we have some Coulomb potential. In the solid, we have bulk and edges. So we really have finite systems. And then, this is my favorite topic, what about geometrical phase effects, so Berry effects? The chemists know this because when you are dealing with molecules, you have conical intersections, and there are also Berry phases. And in solids, this is even more pronounced. So you have this whole community studying topological insulators, topological superconductors, topologically protected edge currents, and that kind of stuff. And I will come back to that in a few minutes. So as an appetizer, I would like to demonstrate what these topologically protected edge currents are. So what we simulated here is a Haldanite flake. So probably you know that Haldane won the Nobel Prize for his model, so the Haldane model. And now we consider a piece of such a material which does not really exist, but it can be implemented in cold atoms, and something similar exists in real atoms. So this is a bit oversimplified model system, but it captures the essential physics. And now we have some edge state in the system because we are in the topologically non-trivial phase. You can see these red dots. And now we apply a linearly polarized laser field in that direction. And let's see what happens. So you see that there is an edge current going clockwise around. And this edge current continues after the laser is off. And now we do the same thing with a perturbation here. So here's a vacancy. We removed 2 hexagons. And in order to illustrate what topological protection means, we do the same thing. So we apply the laser field, which is linearly polarized. Nevertheless, we get a circularly motion or chiral motion. And now usually you would expect, okay, if there is some vacancy or perturbation, if a current comes along, so like here, and crashes into this vacancy, then you would expect probably scattering into the bulk. But this is not what happens here, and this is what is meant by topological protection. And the explanation for this is rather simple. So we all know the Hall effect, where we have an external magnetic field, unlike in the Haldane model. And we want to drive a current from left to right, let's say, but this doesn't work because the electrons go on circles. So this is cyclotron motion. So there is no current from left to right. But at the edges, these electrons cannot perform the circular motion. They crash into the boundary and therefore they skip along. So the net effect is that there is a current to the right at the upper edge and the current to the left at the lower edge. So here we have an insulator inside and a conductor at the edges. And now you can imagine what happens if you put some perturbation here, let's say some vacancy or just dirt, then this current cannot scatter back because the electron would have to move from the upper edge to the lower edge to go back. So it cannot scatter because there are simply no states available. And this is the secret behind the topological protection. And Haldane invented a model where the whole thing works without external magnetic field. So this is a theory talk. So now I would like to derive a theory for high harmonic generation in the bulk of solids. And in order to make this feasible, I restrict myself to 2 relevant bands. And I want to do this without swiping topological effects under the carpet, which is sometimes done in the literature by simplifying too much. And my approximations are the following. So apart from tight binding, I assume many electrons, but non-interacting electrons. I assume dipole approximation, and we don't have phonons yet. So we start with the tight binding modeling. And tight binding means that you have some hopping from one unit cell to the other, from orbital beta to orbital alpha. So these can be 2 lattice sites or 2 orbitals in the same atom, doesn't really matter. And the whole thing is governed by this transition matrix element calculated with these localized orbitals with which you build up your tight binding model. And an example is here for the Haldane model. What are these hoppings? In the Haldane model, there is a nearest neighbor hopping, T1. There is an alternating on-site potential in order to open a band gap in the band structure. And then there is this next nearest neighbor hopping, which is complex. And this mimics, in a way, a magnetic field. So the effect of this complex hopping is similar to what an external magnetic field does in the Hall effect. Another example for such a tight binding model is the Su-Schrieffer-Heeger chain. This is a kind of fruit fly for topological physics. It's the simplest system that has edge states. And originally it was invented for polyacetylene. And the tight binding modeling is as follows. You have 2 hopping amplitudes, V and W. And the system becomes topological if W is greater than V, because then these 2 edge atoms are not properly paired, and you can have edge states here and here. So we investigated this model in the laser field a lot, but I have no time in this talk to present that. So now we do a Bloch ansatz to switch to lattice momentum space. And what is the Bloch ansatz? So we switch from position space to momentum space by making a kind of Fourier ansatz. And now there is a subtle point. There are two possibilities how you can do that. This is wonderfully described in this beautiful book by Vanderbilt. So you can either take the positions of the lattice sites within the unit cell into account by this tau vector, or you can neglect it. And this is just mathematics. You can do what you want. But it turns out if you do the green ansatz, then in the end, the coupling to the laser field really amounts to replace K by K plus vector potential. If you do this ansatz, it's different. And the same for the current operator in the end. If you do this ansatz, the current operator is easy to derive. If you do this ansatz, it's much harder. So if you plug this in, then you will find that your Hamiltonian in K space is diagonal. So there is just a hopping from K to K between different orbitals. And it's now enough to discuss the properties of this Hamiltonian. This is called the Bloch Hamiltonian. And if you have, let's say, two bands, then this Hamiltonian will be a 2 by 2 matrix if you represent it like this. And then in the end, what you have to solve is this eigenvalue problem for a 2 by 2 matrix, or in general, if you have n bands, it is an n by n matrix. So that's the reason why people like to switch to K-space, because you start in position space with a matrix that is infinite times infinite, and then in K-space you have a very small matrix, depending on how many lattice sites you have per unit cell. So now if you calculate these energy eigenvalues for all Ks, you obtain the band structure. And now, as I said, our theory is restricted to systems where a 2 by 2 Bloch Hamiltonian is enough. So just 2 atoms per unit cell. And if this is the case, then you can expand in Pauli matrices, because any Hermitian 2 by 2 matrix can be expanded in Pauli matrices. There are 3 of them. And therefore you have some coefficients, and these coefficients you can collect in a 3 vector, dx, dy, dc. So this is well known. If you calculate the eigenvalue of this, you will find that the energy is actually the absolute value of this d vector. So we have the band structure, and then you can choose eigenvectors. Eigenvectors are not uniquely determined. You can multiply by a phase vector, which is even k-dependent, and this is what people call gauge freedom. In this case, the structure gauge freedom. So as I said, if you choose the right Bloch ansatz, then coupling the whole system to a laser field is easy. You just replace this time-independent equation, which we had here, with the corresponding time-dependent equation. So IC dot instead of eigenenergy times C, and you replace K by K plus vector potential. And this is actually the numerically simplest equation to solve. And in fact, we calculate spectra using this equation, but it doesn't lead to any insight. So in order to see what is actually topological or not, we follow what Barry did many, many years ago. We expand in adiabatically following eigenstates. So you can write down this time-independent Schrödinger-like equation where now the eigenenergies follow adiabatically this time-dependent D. And this is only a good approximation if the driver was incredibly slow. But if you have to do better, you can always expand in these time-dependent eigenstates. So now we have a representation where the coefficient is time-dependent and the eigenstates themselves also. And now you can plug this in and derive the equation of motion for these coefficients. And you will again see this is a 2 by 2 problem, but now these entries are more complicated. And what shows up here are the Barry connections. So here's an intra-band Barry connection. This is, let's say, the conduction band. Here's the Berry connection for the valence band. And then we have interband Berry connections. And of course, as usual, the energies on the diagonal. And now, in the end, we would like to have a Lewenstein kind of modeling. And in the course of the Lewenstein modeling, at some point, we want to make this assumption that depletion is not important, so that the occupation in the valence band is almost 1. And we cannot do this with the alphas because it is only absolute value-wise 1, but there will be a phase rotation because we still have diagonal elements here. So what we do is the usual thing. We transform away the diagonal elements. Usually there is only the energy. So this would amount to make the transition to the interaction picture. But now we also have these Berry connections here, but nevertheless we can transform this away. And then we get an equation of motion for the etas. And now the diagonal elements are not there anymore. So what are these off-diagonal elements now? We can write this down. So there is some phase factor, there is some coefficients, and this is the interband Berry connection written down here. And then the energy difference enters and the difference of the intraband Berry connections. So now we can do this assumption that there is no depletion. So the valence band is just almost fully occupied because there are no diagonal elements anymore. So in the end, if we want to calculate high harmonic spectra, we need the current or the velocity. They are proportional to each other. And again, if we choose the right convention, the right Bloch-Ansatz, the velocity is really the derivative of the Bloch Hamiltonian with respect to momentum in the direction of interest. If you make the other convention, this is not the case. So one has to be very careful here. Now, since our Bloch Hamiltonian is expanded in Pauli matrices and they are constant, of course, we have essentially a derivative of these coefficients organized in this D vector. In the end, we need expectation values, not operators. So we come from the left with C dagger and from the right with C. And if we expand in our eta, then there will be a contribution from the valence band, from the conduction band, and then these interband contributions. So this is written down here. In the valence band, you have the valence band population times this expression. And in the conduction band, the same. Conduction band population times this expression. So people that know the Dirac equation may notice that when you have such a Pauli matrix, this is always related to velocity somehow. Yeah. Expectation value of Pauli matrices. And then we have these interband velocities. They look a bit more complicated with both etas and then here some action and again such an expression. And the interband velocity in the other direction is just the complex conjugate of it. So if you add them up, everything is real, of course. And now comes the straightforward but extremely cumbersome part. I don't show you. Expressing all that stuff in terms of just the D components. So we want to do this because the system under consideration is entirely defined by the components of this D vector. So we need to express everything in terms of these dx, dy, dc, absolute value of D and D perpendicular, which is dx squared plus dy squared. And if you do this, you will find, okay, the usual thing, the intraband velocities are the group velocities multiplied by the populations. This is not surprising. The interband velocity is a bit more complicated. We have some phase factor and then this piece over here. I introduced this calligraphic D, which is kind of Poisson Klammer with just one derivative. You can read here how it is defined. This somehow has to do with the Berry curvature, but it is not just the Berry curvature you find in the literature for the system under consideration. because Berry curvature is there most of the time concept of a single band. And here we have an interband object, V minus plus. So in the end, we Fourier transform, take the modulo square, and if we are just interested in the interband harmonics, we just take the V minus plus and plus minus. And if we can make this assumption that there is no depletion, then we can derive explicitly an expression for this eta in the conduction band. So you don't have to solve a differential equation anymore. And then you plug this in and you have an explicit expression for the interband velocity in terms of the x dy dc. And now if you give me your system defined by the x dy dc, I can calculate this interband velocity and from this the harmonics. So this is written down here again. It looks a bit complicated, but now comes the comparison with the Lewenstein paper. So the structure is the same as the expression for the dipole in the Lewenstein paper, from which you calculate the harmonic spectra in the end, because there is a prefactor at time t, then an integral over t prime, a prefactor depending on t prime, and then e to the power of minus I sum action. And the action is here the energy difference between valence and conduction band. So this would correspond to the ionization potential in the atomic case. And what's new now is this Berry stuff. So this is where topological effects may emerge. So if you have the same equations, you have the same solutions, as Feynman said, or in this case, if you have the same structure of an equation, now you could repeat all things Lewenstein et al. Did in their paper, in particular, writing down saddle point equations. So you may wonder, there is no momentum integration yet, but momentum integration comes into play in the solid case when you integrate over the Brignone zone. So it's really very similar. The only problem is that the saddle point equations are damn complicated, because the dispersion relation is not just p squared over 2, but it can be arbitrarily complicated, and then you plug k plus a. So the dependence on momentum and time is terrible. And probably it's not easy to solve these saddle point equations. You may also note that what you can usually find in the literature for the velocity, so group velocity plus this cross product of k dot, which is a dot, that is the electric field, cross the Berry curvature, looks very different from what I derived here. But you have to note that there are additional assumptions underlying this equation, namely a single band approximation and, for instance, semi-classical wave packet dynamics. And I don't do these approximations in my calculations here. So now, finally, we want to simulate something. So we apply this theory to Haldanite, which is the Haldane model for bulk. And the Ivanov group studied this already. So what I show you now is not terribly new from the physical point of view, but it tests our theory. And this is why I do this. So Silva et al. Showed that you can see the topological phase transition of the Haldane model by looking at the ellipticity of the harmonics. So here's the phase plane. You have this phi, which is the phase of the complex hopping. And here you have the on-site potential. And there is a topological phase transition, which is along this curve. And exactly there, the helicity of the harmonics flip. So you can map out the Haldane phase portrait with harmonic generation and looking at the ellipticity. So now we model this with our theory. Here's again the system in position space. Here in momentum space, you have this graphene-like behavior. And you have so-called K and K prime at K points and M points and gamma points. So K prime is here, K is here, here would be K prime again, and so on. And in the pure graphene case, you have these Dirac cones. And if you introduce on-site potentials, you open the band gap. And if you introduce the next nearest neighbor hopping, you make the system topologically non-trivial. As I said, the input of our theory is just this D vector. And in the Haldane case, the D vector looks like this. There are some vectors which are written down here. I don't have time to go into details. Here's the nearest neighbor hopping. Here's the next nearest neighbor hopping. Here's the on-site potential. And you can plot the band structure. So here we go from gamma to K to M to K prime, which means here from gamma to K, M, K prime, and back. And here we are below the topological phase transition. We have already a band gap. And here we are above. But just looking at the band structure, you don't notice anything special, especially if you focus on this K point. So you can see that band structure-wise, almost nothing happens. So in order to see topological effects, it's not enough to show at the band structure. You have also to consider the Bloch eigenvectors. So now let's look at the dynamics around the K point. So here we started from the K point with an electron. And what is plotted here is the current along the linearly polarized laser direction and perpendicular to it. And now color-coded is the time. So we start from blue, early times, and end up with red, and then the pulse is over. And you can see below the topological phase transition, you have here a clockwise motion. And above the topological phase transition, it is counterclockwise. So you can see that really something changed during the transition, although from the band structure point of view, not much has changed. So now you can imagine if an electron rotates clockwise or counterclockwise, this will definitely have some effect on the helicity of the harmonics. So let's look at the harmonics polarized along the driving laser. And here you see three spectra, and they are all the same, just vertically shifted, but calculated in three different ways. First, with this equation of motion, which does not care about any topological effects explicitly. They don't show up in this equation. Then these equations for the eta, you remember, where we see all the Barry stuff. And this is just to show you that our equations are correct. So you get the same spectrum with a different equation. And then finally, by replacing the valence band population by just unity, and again, you see that almost nothing changes. Then above the phase transition, okay, the spectra look a bit different, but qualitatively, you cannot tell whether this is topological or not. Then the perpendicular current, so the harmonics with the polarization direction in perpendicular direction. This is what I should say. Again, calculated in the three different ways with the same result. So just looking at the harmonic yield, you cannot tell what is going on. Above the phase transition, it doesn't look very different. But if you look at the helicity, you can see, okay, it is not that simple. Different harmonics behave differently. But let's focus here on that bunch of harmonics, so from 10 to 20. We have mostly a helicity phase of -π/2, again calculated with the three different equations. And above the topological phase transition, it really flips to +π/2. So this confirms what was also observed by the Ivanov group. I would love to show you now results for all the other points here in the Brignon zone, because the behavior is very different at the K prime point and yet different at the M point. So in the end, we have to integrate over the Brignon zone, and then it depends on which point is dominating. So let me summarize what's new in solids. I hope I could convince you that it's extremely rich and at times counterintuitive electron dynamics that is taking place in solids. And I like working in that field because now we make contact with condensed metaphysics, and usually new exciting stuff emerges at the boundary between different fields. And we now encounter all this fancy stuff condensed matter physics is concerned with, including topological insulators, topological superconductivity, or even more exotic stuff like Majorana fermions. But the question is, what can we strong field attosecond people contribute? So we can say, yeah, we can create new electronic structure by laser tracing, but this is actually not new. There is a whole community dealing with flake topological insulators. There's a recent proposal by, again, the Ivanov group on subcycle Velitronics. So Velitronics means that you use the K and the K prime point to implement a qubit, and then you can manipulate this qubit with ultra-short laser fields. That's the idea. And then potentially very important for faster electronics is ultra-fast light wave electronics, because if you have these topologically protected edge currents, they are ballistic, they don't scatter, so you can modulate them with arbitrarily high frequency. And usual electronic currents would just scatter and dephase, but not these topologically protected edge currents. And I do all that stuff because for me it's just a new playground with lots of things to be done. So thank you for your attention.
Thank you, Dieter, for a very nice talk. Oh my God, so many equations, but very nice. I see two raised hands. Maybe Manfred goes ahead first.
Thank you. Thank you, Dieter, for the nice overview. In the very beginning, you made this statement that rescattering is kind of automatically included in the Bloch states. I was wondering what that really means, because rescattering to me, it means something like return of an electron to a spatially localized hole. And I don't, it's not obvious to me if that is automatically included in this description.
Yes, so first, let's look at it without external laser field. Then probably you agree that some electron which moves in a periodic potential is covered by this Bloch Hamiltonian, right?
Yes.
And now if you add the laser field, it really turns out that if you use the right Bloch ansatz, you can go back to position space and couple to the laser field there by the Peyl substitution, as it is sometimes named. And then you again transform to K-space, and you see that in fact what you have to do is just replace K by K plus A in this Bloch Hamiltonian if you do the right Bloch ansatz. And this is what I meant when I said it is automatically included, because the laser coupling is so simple and you don't have to think about rescattering in position space then, which is much more complicated.
Okay, thanks.
Jens, I don't hear you, so, but...
Yes, sorry, I said go ahead.
Yeah, thanks. So I have a question. So this is a very elegant derivation. So, but when I understand that it's very complex to go beyond two bands. But I mean, like I would ask you about your third perspective. So a real solid consists of so quite several valence bands would contribute, and conduction bands lie very dense to each other. Like real solids, it's even much more complex when it's really I mean, like really just two bands. So have you ever thought what would change, what would happen? I mean, whether it would be very different if you take into account a real band structure, a real solid.
Yes, so actually we started off with time-dependent density function theory, where you have all the bands, and just to find out later that qualitatively all the results we get are the same as from these tight binding models. And then at some point we decided to continue with tight binding because it is 10,000 times faster on the computer. We also did systems with 4 bands, nano ribbons. And in fact, there are new effects. if you have 4 bands and topologically non-trivial dynamics. The question is whether you can reduce it to 2 effective bands that close their band gap. Because whenever you have a topological phase transition, you close a band gap and you reopen it again. So perhaps it is possible to reduce the problem to, again, an effective 2-band model, but we don't know yet.
Yeah, thanks.
Okay, and there was a question by Maciek Lewenstein. Maciek, go ahead.
Okay, so this is contributing to the discussion about the rescattering. So in 2017, we have published a paper in Physical Review X in which we essentially developed the same theory of high harmonic generation for solids, but using an equivalent description of the valence band using Wannier functions, which are localized in space. And then, of course, the picture is exactly the same as in the atoms. So in principle, of course, Dieter is right because the 2 bases are equivalent. On the other hand, in the Wannier description, of course, you see the trajectory is much more similar to those which are atomic, even though and dispersion energy is very complicated, as you said, and etc. But still, you have this thing that your electron is leaving the Wannier orbital and is coming back to this one or to the one, not to the same part of the orbital which is in the other side of the lattice. So it's like in molecules that you can recombine in different places. But all of this, of course, if you do everything exactly, is completely equivalent. So the Bloch picture contains the scattering. In practice, it's not, because in practice, you always have to do some more approximation to handle. But it's approximations which may be destroyed.
Yeah.
Thank you.
So I totally agree. I forgot to mention the option of Wannier functions. So this is essentially another Fourier transform. Yeah, sorry.
I have a quick question, Dieter. So you mentioned when you made the comparison with Maciek's or the Lewenstein model that was published there, you made the comment that, of course, the difficult thing is the dispersion relation at some point, and one has to probably decide, depending on the system that you want to describe from case by case, how to do that, right?
Yeah, so we tried several things. You can expand in the vector potential so that only A and A square shows up. This is already something which is more similar to the usual Lewenstein model because there is also A and A square. But still, it is too complicated, a too complicated function of the momentum. And now if you also make a Taylor expansion around a certain K point, I think you lose the interesting physics. Because, okay, you can describe the surrounding of a K point always up to 2nd order, but then the whole fun is gone. Yeah.
Yeah.